So let us continue our discussion on Galilean transformation by solving these sample problems. So the first problem, we have a passenger in a train moving at 30 meters per second passes a man standing on a station platform at t prime equals 0. 20 seconds after the train passes him, the man on the platform determines that a bird flying along the tracks in the same direction as the train is 800 meters away. What are the coordinates of the bird as determined by the passenger? So for this problem, we are asked to find the coordinates of the bird as determined by the passenger on the train. So we start by writing the coordinates of the bird as assigned by the man on the platform. So the man on the platform will see that the bird is at x, y, z at time t. So we have 800 meters, and then we have our y and z, 0, and then we have 20 seconds. Now for the passenger on the train, the coordinates will be the primed coordinates. We have x prime, y prime, z prime, and t prime. So to find x prime according to the Galilean transformation is just equal to x minus vt. So this is equal to 800 meters minus the speed of the train, which is 30 meters per second, multiplied by the time, which is 20 seconds. So this is equivalent to, this is 600 meters. So we have 200 meters. Okay, so we have this one, x prime, 200 meters, and then your y prime is 0, your z prime is 0, and then your t prime, according to the Galilean transformation, time is absolute, so t is just equal to t prime. So we have 20 seconds. So this is the coordinates of the bird as assigned by the passenger on the train. Okay, so let's move on to problem number 2. So referring to problem number 1, 5 seconds after making the first coordinate measurement, the man on the platform determines that the bird is 850 meters away. From this data, find the velocity of the bird as determined by the man on the platform and by the stranger on the train. Okay, so for this problem, the coordinates assigned to the bird at the second position by the man on the platform, we can represent it as x sub 2, y sub 2, z sub 2, and t sub 2. So this is equal to 850 meters. And then this one is 0, 0. And then for your t2, this is equal to 20 seconds plus 5 seconds. So we have 25 seconds. Okay, so this is the coordinates of the bird as assigned by the man on the platform 5 seconds after making the first coordinate measurement. Hence, the velocity of the bird as measured by the man on the platform is just equal to the change in displacement with respect to time. Okay, the velocity along the x, shall we call it u sub x, is just equal to the change in displacement along the x with respect to time, or the change in x divided by the change in time. So we have x final minus x initial divided by t final minus t initial. So our x final is 850 meters minus 800 meters divided by our t final, which is 25 seconds minus 20 seconds. So we have this one, 50 meters divided by 5 seconds. So u sub x is equal to 10 meters per second. So this is according to the man on the platform. So this is the velocity according to the man on the platform. Okay, and then we can also obtain the primed coordinates or the measurements made by the passenger on the train after 5 seconds. So we can call it x sub 2 prime, y sub 2 prime, z sub 2 prime, and t sub 2 prime. Okay, so x sub 2 prime, x sub 2 prime can be obtained by this one, x sub 2 minus v times t. X sub 2 minus v times t sub 2. So x sub 2 prime can be obtained by this equation. We have x sub 2, which is 850 meters, minus v, this is the velocity or the speed of the train, and t sub 2, which is equal to 25 seconds. So substituting all the values, we have 850 meters minus 30 meters per second, the velocity of the train, multiplied by 25 seconds. So our x sub 2 prime is we have 850 meters minus 30 times 25. Okay, so this one is 750, so we have 100 meters. Okay, therefore, our prime coordinates in the second measurement after 5 seconds is we have 100 meters, 0, 0, and then we have t sub 2 prime, which is just equal to 25 seconds. Alright, and then to find our u sub x prime, so this is the velocity of the bird in the second measurement as measured by the man on the train or the passenger on the train. So we have u sub x prime is just equal to delta x prime minus delta t prime. Okay, so delta x prime x final is equal to 100 meters. X final is equal to 100 meter minus x prime initial, which is 200 meters, divided by the change in time, 25 seconds minus 20 seconds. So this is equivalent to, so we have negative 100 meters divided by 5 seconds. So this is equal to negative 20 meters per second. So this is the velocity of the bird as measured by the passenger on the train. So notice that the passenger on the train obtained a negative velocity while the man on the platform obtained a positive velocity. Okay, for problem number 3, we have this one. A sample of radioactive material at rest in the laboratory ejects 2 electrons in opposite directions. One of the electrons has a speed of 0.6 c and the other has a speed of 0.7 c, as measured by a lab observer. According to classical velocity transformations, what will be the speed of one electron as measured from the other. So for this problem, we let observer O to be at rest with respect to the laboratory and observer O prime be at rest with respect to the particle moving with speed 0.6 c. So using the Galilean velocity transformation, we have u sub x prime is equal to u sub x minus v. So this is equal to negative 0.7 c, because take note that the two electrons are moving in the opposite direction. Minus, we have 0. Minus 0.6, so we will obtain negative 1.3 c. So this problem illustrates that velocities greater than the speed of light are possible with the Galilean transformation. Later, we will see that this result is inconsistent with special relativity. For problem number 4, we have a train that is moving with a velocity of 60 miles per hour passing through a railroad station at 12. 20 seconds later, a bolt of lightning strikes the railroad tracks 1 mile from the station in the same direction that the train is moving. Find the coordinates of the lightning flash as measured by an observer at the station and by the engineer of the train. So in this problem, we are given with the velocity of the train, which is equal to 60 miles per hour. And then, in order to find the coordinates of the lightning flash as measured by the observer at the station, we need to know the x, y, z, t coordinates. So we can call the observer on the station as observer O. So for observer O, he can see that the lightning flash is at xyzt. And for observer O prime, so this observer O prime is the engineer of the train. So he can see that the coordinate is at x prime, y prime, z prime, and t prime. Now take note that both t and t prime are equal. T is equal to t prime, which is just equal to 20 seconds. Now x, for x, uh, since the lightning strikes the railroad tracks 1 mile from the station, and the observer O is at rest with respect to the station, then x is equal to 1 mile. So x is equal to 1 mile. And then there is no movement along the y and z axis, so both y and z components are 0. And for x prime, so the x prime, we can get x prime by using the Galilean transformation. So we have x minus v times t. So this is equivalent to, we have 1 mile minus the velocity of the train, which is 60 miles per hour, multiplied by the time, which is 20 seconds, converted to, we convert this to hour. So we have 20 seconds multiplied by We have 1 hour is equivalent to 3,600 seconds. So this is equivalent to 1 over um, 180 hour. Okay, so this is 1 over 180 hour. So evaluating, we will get, uh, we have 1 mile minus, this is 1/3 mile. So we will get 2/3 mile. Okay, so this is your x prime. So therefore, as seen by the observer O, we have this coordinates, um, 1 mile, 0, 0, and then we have 1 over 180 hour. And for observer O prime, we have this coordinates 2/3 mile, 2/3 mile, 0, 0, and then 1 over 180 hour. Okay, and the last problem that we will discuss is this one. Consider a mass attached to a spring and moving on a horizontal frictionless surface. Show from the classical transformation laws that the equations of motion of the mass are the same as determined by an observer at rest with respect to the surface and by a second observer moving with constant velocity along the direction of the spring. So the equation of motion of the mass as determined by an observer at rest with respect to the surface. Okay, so we have this equation. F is equal to ma, mass times acceleration, where F for this system is just equal to minus k x minus x naught. So x being the final position of the mass and x naught is the initial position of the mass. And the acceleration is equal to uh, the second derivative of x with respect to time. Therefore, we can write this as minus k x minus x naught is equal to m d squared x over dt squared. Okay, now using the classical Galilean transformation, we have x, so we have x is equal to x prime plus vt, and x naught is equal to x naught prime plus vt. Now we can also get the second derivative of x with respect to time. So from this equation, we can get the second derivative of x with respect to time. So the acceleration A is just equal to the second derivative of x with respect to time. This is just equal to the second derivative of x prime with respect to time. Now, if we substitute these equations, uh, 1, 2, and 3 into our equation of motion, then we will have this minus k, your x is x prime plus vt Take note that your t is just equal to t prime minus x naught prime, x naught prime minus vt. So this is equal to m dx prime squared dt squared. So we have a prime here. And canceling out plus vt and minus vt, so we are left with minus k. We have x prime minus x naught prime is equal to m d squared x prime over dt prime squared. Okay, so this is the equation of motion as determined by an observer that is at rest with respect to the surface, and this one is the equation of motion as determined by the second observer moving with constant velocity along the direction of the spring. So since they have the same form, then this means that the equation of motion is invariant under the Galilean transformations.